Today we're going to look at some different problems that require implicit differentiation, but we're actually going to take it a bit further. In this first example, it's asking me to find all horizontal and vertical tangent lines to this curve. In order to find tangent lines to the curve, we know we need to find the derivative. So this is a long problem. We have 8x plus 2y dy over dx minus 8 plus 4 dy over dx. This derivative is 0 and this equals 0. Collect our dy over dx's on one side. And I'm going through this rather quickly because we have been doing implicit differentiation for 2 days now, and we should be getting good at this. Move the negative 8 to the other side, which gives me a positive 8. Move the 8x over, I get a minus 8x. We are now going to factor out our dy over dx's. When we factor out our dy over dx's, we are left with 2y plus 4. Now I'm going to divide by that 2y plus 4 to get my final answer for dy over dx. So in general, we could find the slope of any tangent line to the curve using this 8 minus 8x over 2y plus 4. Let's go ahead and find those specific ones that we're talking about. Let's go ahead and do the vertical tangent lines. We haven't done a whole lot of vertical tangent lines, I don't think any. But what would that mean? Well, that would be where our bottom is equal to 0. So what I'm going to do is I'm going to look at the bottom of the slope of the tangent lines, and I'm going to figure out where is that undefined. Well, quite simply, that would just be where y is equal to negative 2. That doesn't tell me the actual points at which this is going to occur. So all I really have is that I know it's going to be at negative 2. Now I've done this problem before, so I actually know there's going to be 2 points that come up, but let's go ahead and assume there's just one for right now. How do we get our x values? Well, we have to take that y value and plug it back in to our original question up here. So we now have 4x squared, plug in our negative 2 for our y squared, which was right here, minus 8x plus 4 times negative 2 plus 4 equals 0. That gives me 4x squared plus 4 minus 8x plus negative 8 plus 4 equals 0. Well, 4, 4, and negative 8 create 0. Factor out of 4x, and we're left with x minus 8. Oops, let me take that back. That'd be x minus 2. I already factored out the 4. Equals 0. So my x values end up being 0 and 2. So my 2 points would be 0, negative 2, and 2, negative 2. Those are the answers for the vertical tangent lines to the curve. Now I still need to find the horizontal tangent lines to the curve. So I'll go back over here, talk about where the horizontal lines would be located, and those would be when the top is equal to 0. So let's see, we have 8 minus 8x equals 0, and we end up getting 8 equals 8x, and x is equal to 1. So my x coordinate is 1, but in order to find my y coordinate, I have to take that and plug it back into the original. So I have 4 times 1 squared plus y squared minus 8 times 1 plus 4y plus 4 equals 0. That will allow me to solve for y. So I have 4 plus y squared minus 8 plus 4y plus 4 equals 0. 4, negative 8, and 4 makes 0. Factor out a y. I'm left with y plus 4 equals 0. So my y values are 0 and y equals negative 4. That creates 2 points. 1 comma 0. Okay, there's my x, 1, and there's my y, 0. And the other point is 1 comma negative 4. This was quite a lengthy problem. We can discuss this further together. Okay, continuing on with some harder problems that involve implicit differentiation. I want you guys to go ahead and put this on your graphing calculator and graph these two graphs. I'm going to go ahead and tell you where their intersection points are just really quickly because those are the 2 points we're going to be looking at to figure out whether or not they're orthogonal. I'll explain orthogonal a little bit further here after I get their points of intersection. Again, you guys can use your graphing calculator to do this. I'm going to just do this visually by making a substitution. I'm going to say 2x squared plus 3x cubed. I replaced my y squared with an x cubed equals 5. I can then see that at x equals 1, there's going to be some points of intersection. Those 2 points that you guys are going to see on your graphing calculators, or I can just do them by hand, are 1, 1, and 1, negative 1. What we want to do is at those points, we want to see if the tangent lines are perpendicular to each other. So we're going to see if the slopes of the tangent lines are negative reciprocals. So I'm going to take the first curve, y squared equals x cubed, and I'm going to find, in general, the derivative, meaning the slope of the tangent line, and this could be used to find it at any point. So I have 2y dy over dx equals 3x squared, and then I'm going to divide by 2y on both sides. That gives me 3x squared over 2y. That is the slope of the first curve at any certain point. The slope of the second curve would be found by finding its derivative of 4x plus 6y dy over dx. The derivative of 5 is 0. Solve for dy over dx. I have 6y dy over dx equals negative 4x. Divide by 6y on both sides. I end up getting negative 2x over 3y. I did reduce my 4/6. Now, in order to figure out if their slopes are negative reciprocals of each other, we need to actually figure out what is the slope at 1, 1 for each of these. So, when we're talking about the point 1, 1, the slope of the first curve would be slope of first curve would be 3 times 1 squared over 2 times 1, or 3/2. The slope of the second curve at 1, 1, okay, would be this one. It would be negative 2 times 1 all over 3 times 1. So we get negative 2/3. Notice how these two slopes are negative reciprocals of each other. They are negative reciprocals of each other. And I can now say that these are orthogonal at 1, 1. We only need to check then at 1, negative 1. So when we're talking about the point 1, negative 1, the slopes of the first curve, the slope of first curve, we're going to plug in 1 and negative 1. So I'm going to have 3 times 1 squared over 2 times negative 1. This gives me a slope of 3 over negative 2. And the slope of the second curve, when I plug in 1 and negative 1, gives me negative 2. I'm plugging back in over here, plugging in 1 for x and negative 1 for y. That gives me a negative 2 over a negative 3, which is a 2/3. So again, we get two slopes that are negative reciprocals of each other. So I have shown that these two graphs at those intersection points, that the graphs are orthogonal at those points of intersection. Okay, on this problem, we're going to use implicit differentiation to verify that the two families of the curves are orthogonal, where C and K are real numbers. So orthogonal again means that the tangent lines to the curve are going to be perpendicular to each other. So let's define perpendicular a little bit differently. We have been saying that perpendicular lines have slopes that are negative reciprocals of each other. That is very true. 2/3 and negative 3/2 are negative reciprocals of each other. We can also say that when we multiply those negative reciprocals together, we get a product of -1. We will be using that knowledge to be able to verify that these two families are orthogonal. So in this first curve, I'll go ahead and find the derivative of it. And the derivative would be 2x plus 2y dy over dx equals 0. Solve for dy over dx quickly. Dy over dx ends up being negative 2x over 2y. But I'm going to simplify that, and I get negative x over y. Now I need to look at my second curve, y equals kx. Take the derivative, dy over dx equals k. Now using this knowledge, I'm going to talk about multiplying those two slopes together. And hopefully that we'll find out that the two slopes, when we multiply these two together, the product of those equals -1. So does it equal -1? That's what we're really asking ourselves. Well, right now it doesn't. But if I look a little bit further, I'm going to be able to replace this y. This y can be replaced with a kx. So I'm going to have negative x over kx times k equals -1. What did that now allow me to do? Well, it allows me to cross-reduce my k's. It also allows me to reduce my x's. So I do get that -1 equals -1. So I have verified that these are orthogonal. Next problem, I'm not going to have the time to talk about differentiating this with respect to x. We have done nothing but that. That's when we solve for dy over dx. What we're going to do different is we're going to solve this with respect to t. So none of these variables are t's. So every time I take the derivative of something, I'm going to have to put dx over dt or dy over dt. Those are the two variables we have in this problem. So we're going to take the derivative of this x, which would be 2x, and we're taking the derivative of x with respect to t, so I'm adding in my dx over dt. I'm going to change this to plus the opposite. Otherwise, I'm going to end up losing my negatives, and that will be a problem later. So strongly urge you to change your signs to plus the opposite, especially since we're doing a product rule. So we're going to do first times the derivative of the second. The derivative of the second is 2y. This isn't a t, so I have to write, I'm taking the derivative of y with respect to t, plus the second times the derivative of the first. The derivative of the first is -3. This wasn't a t, so I have to say I'm taking the derivative of x with respect to t. Plus the derivative of y cubed is 3y squared. It is not a t, so I have to write the derivative of y with respect to t, and then equals 0. I will not be able to solve for just dy over dt or dx over dt, so what I'm going to do is I'm going to collect my dx's over dt on one side and my dy over dt's on the other. So looking at this problem, I have really 2x dx over dt plus -6xy dy over dt plus -3y squared dx over dt plus 3y squared dy over dt equals 0. I'm going to keep these two dx over dt's on the left-hand side. 2x dx over dt minus 3y squared dx over dt equals, I'm going to move this other 2 to the right-hand side. So I'm going to have 6xy dy over dt minus 3y dy over dt. And that is as far as I'm going to be able to take it.